Hey everyone, today we're looking at gravitational fields, and I think we've been talking about gravity a lot, but now we want to stress the idea that gravity is a field force. It modifies the space around it, it warps space-time, and the more mass you have, the more warping you get. The more warping you get, the more force an object feels when you place it in that gravitational field. So for masses, the gravitational field is always pulling inwards. It's always an inward pulling force. So it's always directed towards the center. No matter which part of the sphere you're looking for, it's always pointing in that direction. So what we want to focus on is what is the gravitational field strength? What is the vector quantity of this gravitational field? And the way we can do that is that all objects would accelerate in this gravitational field due to their location from the mass. So here's how we're going to do that. We're going to take the gravitational force and divide by some test mass. Any mass that you want to put in that gravitational field. Let's see if we can find out how strong the field is. So gmm over r squared is the gravitational force. We're going to divide that by a test mass. This test mass is any mass we put in the gravitational field. So that means that up here, this is the Earth and the test mass. I can cancel out the test mass and just leave myself the gm over r squared, which looks very similar to that gravitational acceleration we calculated for each planet. And it's exactly that. The gravitational field strength is the gravitational acceleration for each planet. And it does drop off by a 1 over r squared value, just like force. How do we put units to this? Well, if we want to do units to this, you've got the newtons meters squared per kilogram squared multiplied by 1 mass up top now, just the planet, and divided by meters squared. So doing that, the meters squared cancel, and you're left with newtons per kilogram. So that's one way you can do the gravitational field strength unit. But if you take what a newton really is, remember newton is a mass times an acceleration, you're going to knock out that kilogram, and you're going to give yourself units of meters per second squared. So the gravitational field strength is always radially pointing inwards, no matter where you are from the object, and it's independent of the masses that are placed in the gravitational field. It all depends on the mass that you are focusing on and which one you're falling towards. So let's try this. We've got two masses, mass 1 and 3. They're separated by a 5-meter distance. The question is, what is the gravitational field strength at the 2.5 meter mark, I guess in the j direction, since these masses are up and down. So let's draw the scenario. So here's our scenario. 1 kilogram mass, a 3 kilogram mass, 5 meters apart from each other. I want to know the gravitational field strength right at this moment. So the way that I can do this is I can say that the total gravitational field strength is the gravity from mass 1 plus the gravity from mass 2. And to test that, I'll put some little yellow blob there. That test mass is going to be pulled by both masses. It's going to be pulled downwards by the 1 kilogram mass, and it's going to be pulled upwards by the 3 kilogram mass. Now I drew the 3 kilogram mass force larger than the 1 kilogram mass because it is attracted more to the 3 than it is to the 1, and we're in equal distance scenarios here. So going back to our equation, the gravitational field strength is just gm over r squared. So you use the gravity constant, use 3 for your mass, and a distance of 2.5 squared, and then do that again for the 1 mass. The gravitational field strength for mass 1, we'll call this mass 1, is upwards, so I'm going to leave that positive, and the gravitational field strength from mass 2 is negative, since it's downwards. So crunching your numbers, this is what you should get. So you see the 3 kilogram mass is pulling up with 3.2 to the negative 11th newtons per kilogram for its gravitational field, and the smaller mass is down at negative 1.06 to the negative 11th. Combining those, you get up a net gravitational field of 2.133 to the negative 11th. The net gravitational field is positive, so putting any mass at that location, the middle of those two masses, the object will accelerate towards the bigger mass because it has a bigger warp in space. The question they love asking sometimes is, okay, if that middle location is dominated by the big mass, where then could you put, where in this space would you want to put something so that both masses pull on it equally so that it doesn't really move? So when you think about it, you're trying to make your gravitation or net gravitational field add up to 0. Gravity from mass 1 pulling up, and you got gravity from mass 2 pulling down. Just thinking through it rationally, you'd think, well, if the midpoint is leaning more towards the big mass, I'm going to go closer to the small mass. Increase my distance from the big guy and decrease my distance from the small guy. This should be where my 0 point is. So if you're going to do that, and I wanted to find that location, I'm going to call that whole distance there x. So remember that this was 5 meters apart. So if I want to figure out how far away that is, let's call the distance from one mass to the other one x. So I'll say that from the one mass, we are x distance away from this point of no gravity, minus the gravitational field from mass 2. Now the distance for mass 2 is a little trickier. You've got to do 5 minus x, and don't forget to square. Setting those two gravitational field strengths equal to 0, you should have enough information now to go ahead and solve for where that location is. So there is a point between two masses where you don't feel anything. On the way to the moon, when the astronauts got closer to the moon than they were from the Earth, there was a location where they were pulled equally in both directions from the Earth and the moon. They were at that location where there is no gravity in space. There is gravity, the net result was no gravity. Now what we want to do is see how the force of gravity and how the gravitational field strength change when we have different shapes and distributions of masses. So in this one, we've got a hollow sphere. Assuming that all the mass is on the outside of the sphere, we want to figure out what is the force of attraction. So if I put a mass here outside of that shell of mass, we are separated by a distance of r. If I want to calculate our gravitational field, I need to know g, mass 1, mass 2, and have a distance of separation. So anywhere outside the sphere, I get a force of gravity that looks just like we're used to. Close to the planet, the force of gravity is very, very strong, and far away from the planet, the force of gravity drops off very quickly like the butter gun. But now let's talk about us going inside the sphere. When we go inside the sphere, the mass at the top of the sphere pulls up, the mass at the bottom pulls down, right pulls to the right, the left pulls to the left, and overall that mass would actually feel no force because it's attracted equally to all sides of the shell. So it'd be really cool that if we could make a shell of mass, so if we could get a mass big enough that was about the mass of the Earth, and you crawl inside the shell, you could float around with feeling no net effect from anything. Once you started moving from one side of the shell to the other, you would just cruise at a nice steady speed because the force of gravity cancels out in all directions. Now some of you might say, well, my example was just at the center. What if I'm really close to here? If I'm close to the edge, there's got to be some gravity. And I would say, well, yes, you are strongly attracted to this edge of the shell. However, all the way over here at the back end of the shell, there's a lot more mass that is further away. So when you add up and you average the attraction of every single piece around the shell from your test mass, all of these pieces are going to add up to give you 0 net force. So inside a shell of gravity, you would have absolutely no force on you whatsoever. So it's a really cool experiment or thought idea of what would happen in that scenario. And here's your graph of that. No gravitational force inside the shell. Once you're outside the shell, it acts just like everything you've ever seen. But now let's talk about a solid sphere, similar to what Earth is. Now Earth is not perfectly solid. It does have different layers and densities all the way through. But let's do the same experiment we did last time. I put my mass out here. I have mass 1. I've got mass of planet. And I've got a distance of separation between the two of us. So outside the sphere again, it's no different. It's still GMM over r squared. But what happens when we start diving into the shell? Well, when we start diving into the shell, let's say the dotted line they gave us right there, some of the mass is between you and the Earth, and some of the mass is outside of you. When we do the force of gravity calculation, that distance is from the center of mass 1 to the center of mass 2. So really, you don't even have to care about the mass that's outside of you. And how's that going to work? Well, if we wanted to calculate that force of gravity, let's do that. For the force of gravity, first m is your mass, second mass is the rest of the mass from the center of you, or from you to the center of Earth. And we're going to divide that by little r. Little r is that distance there from the center to your location as you start digging into the Earth. Well, how do we do this? Well, we have to assume a couple things here. We have to say that Earth has a particular density. That's a particular mass per unit volume. And if we assume that the mass or the density is constant all the way through the Earth, that means that no matter what volume of the Earth I have, I'm still going to get the same ratio of mass per unit volume. The density here must be the same density for the entire solid sphere. So let's set those two densities equal to each other. I'm going to say that, okay, the enclosed mass divided by the enclosed volume equals the total mass over the total volume. All right, if we're going to do that, I want to solve for the enclosed mass so I can put it into my force of gravity equation. So solving for the mass enclosed here, I have the total mass of the planet, then I have 4/3 pi big R cubed for the entire volume of the planet, and on the top I have 4/3 pi little r cubed. Well, the things that can cancel for us are the pi's and the 4/3, so you're left with this ratio now of little r cubed to big R cubed. So let's put that back into our force of gravity equation. So here's what we got. We got force of gravity is big G mm over r squared. We replaced the mass center of the Earth to you with big M, mass of the whole planet, little r squared over big R squared. And you're going to get some more cancellation here. You're going to get the whole r squared to go away, leave one r behind. So when you do that, now we've got a force of gravity equation here that is mass 1, mass 2, so you and the planet, but now it's all dependent on this little r distance, your distance from the center of the Earth out. I mean, if you get to the radius of Earth, little r just becomes big R. And now we're back to GMM over big R squared. But if you're not there, then you have less and less distance, less and less radius. Think about it. If you go all the way to the center of Earth, r becomes 0. And if there is no radius right here at the center, you feel no gravitational force because everybody cancels out. Everyone pulls equally on all sides of you. So the force of gravity equation is linear on the way into a solid sphere. There's no gravity at the center of the Earth, and as you start to climb out of the Earth, gravity gets stronger and stronger and stronger. As soon as you hit that surface, gravity goes back to GMM over little r squared, just like we did before for any gravitational attraction. So you get some odd things happening when you have different gravitational fields. And again, gravitational field strength follows the same thing. The GM over r squared is from the surface outwards, but when you climb into the Earth, it linearly gets lower and lower as you get towards the center, or if you climb from the center out, the gravitational acceleration towards Earth gets bigger and bigger. So gravitational fields, again, come from the warping of space and time, and there's a lot of fun scenarios you can come up with, like we said with the hollow shell of mass, that you could jump into this hollow shell and just float around because of equal attraction in all sides. Or some things that people like to do is think, well, what if I dug a hole straight through the Earth? What would happen if I could just jump into that hole? Well, many people have made many videos on that. I'll leave you one here to enjoy and watch, and we'll talk about this next time.